So good morning. Thank you very much, Charles. We are going to present a new P2P SMPC protocol for federated learning using Flower. My name is Sofia. My colleague is Petros. I will give the context because this work has been conducted within the Synthema project, and Petros will follow up presenting our innovative approach. So what is Synthema? Synthema is a synthetic and methodological data over federated computing frameworks. It's an Horizon Europe project that focuses on developing and validating artificial intelligence models for clinical data anonymization, synthetic data generation in rare hematological diseases. And this is the keyword, actually, the rare hematological diseases. So the main aim of Synthema is to generate reliable, high-quality synthetic data that then can shape new virtual patients to further enhance the diagnostic capacity, assess treatment options, predict outcomes in such types of diseases. But the main challenge in this domain, the health domain, and we heard a lot of actually talks in the health domain addressing similar challenges, is that they suffer from a relatively low number of patients, and this means data scarcity. And also they suffer from data silos in unconnected clinical sites and registries. So one cannot combine these data that are crucial in order to generate actually reliable and performant AI models. So this scarcity and fragmentation of data prevents researchers from acquiring this sufficient and quality data for basic and clinical research, and at the same time they're able to address data protection and privacy concerns. This was actually the driver for then using federated learning and actually secure federated learning. The mission, of course, on Synthema is to set up this cross-border distributed hub. We are halfway in the progress of the project. You see here a distributed ecosystem where we have the different clinical sites that we require. We harmonize the data in OMOP, a deep to OMOP mapping we do. And then, of course, federated learning runs across the distributed cross-border hub to generate the synthetic data generation models, as well as anonymization models. This is done in this way in order to tackle the GDPR constraints that we have, and we heard also other talks discuss about this. So what we propose is to develop a secure and privacy-preserving federated learning in order to facilitate the collaborative training of generative AI models without the need, of course, to share or distribute to third parties reward-sensitive health data. We actually have a collaboration with Flower, and we are capitalized on Flower. Synthema is running a Flower Next pilot program application, and now Petros will present our approach primarily on the SMPC part of federated learning. So the floor is yours.
Hello, my name is Petros. I'm a machine learning engineer for Netcompany-Intrasoft, and our approach to the problem is secure multi-party computation protocol for federated learning. So everything started from some key observations we did. We found out that some limitations were very apparent in almost every federated learning scenario. So first of all, in almost every federated learning application, sensitive data privacy is crucial because data may leak or be inferred during training and network communication. We have significant literature demonstrating membership attacks, gradient leakage attacks, etc. And the main issue, if we see it on an abstract level with federated learning, is the single point of trust, because the centralized aggregation always happens using an aggregation server, which is a single point that there has to be trusted. And here SMPC comes to the rescue. SMPC is a general framework allowing to compute functions over shared values that are secret. In our case, these secret values are the parameters learned from the models, and they are held by different peers. And in this way, we allow computation of functions without actually revealing them. Our implementation is based on additive secret sharing, and the key properties that such an implementation offers are that no party learns others' raw secrets, and assuming correct implementation, it provides guarantees that the calculations are performed faithfully, and it even works with a significant number of malicious participants. It is still secure. So first of all, a word about additive secret sharing. If you're familiar with security, you have probably heard before. So it's a framework, a general technique used to divide any secret value into multiple parts. We then share each part of the original secret value to several participants. And in this way, we ensure that the control over the secret is distributed among various peers and not held by one entity. So in the Federated Learning framework, this is the architecture we propose, a peer-to-peer network of clients that communicate with each other, and of course the aggregation server. So here's the process, the algorithm that we use. So each client splits the parameters learned locally after a training round, assuming a network of 6 peers into 6 pieces. Then each client keeps one part for itself and distributes the rest and -1 parts. Then each client aggregates locally the received shares with the one held by itself. And finally, each client sends the locally aggregated parameters to the aggregation server that performs the federated averaging, executes the federated averaging algorithm, which is still robust and holds because the sums remain the same. And obviously, at the end of the round, the server sends back, the aggregation server sends back the global model in order for a new round to begin. So the security and privacy guarantees provided by our method is that no individual share is able to leak updates of the model that may lead to inferring private data. And the aggregation server also cannot infer from where the updates and the parameters originate from. Thus, we could say, despite it is a bit bold, that the server, the aggregation server, can be considered untrusted. It is very resilient to collusion. In our case, many clients may be malicious and we still have security. And it can be easily combined with differential privacy to further enhance security. So we did a bit of experimentation on the MNIST dataset. So you see that the training time using the SMPC protocol is significantly larger, especially as we increase the number of clients. This is because the peer-to-peer network is actually a fully connected graph. So by increasing by 1 its size, we have to maintain n-1 connections. The yellow area is the amount of time took at the establishment at the beginning to establish the peer-to-peer network between the clients. So we do expect, based on math, that the SMPC training time will increase exponentially as we increase the clients. And there are significant challenges and open issues, as well as directions for future work, probably. So there is definitely increased network communication complexity. There is significant message passing in the peer-to-peer network. There are significant dropout issues. What if we miss one peer? In our simple case, if we miss a peer, we cannot reconstruct the parameters correctly. There are significant parallelism and synchronization issues. Each peer must wait until receiving all shares, which makes the process significantly slower. And there need to be constantly multiple threads or processes running in order to handle both communication and training. Thank you very much. On this link, you can find the code on GitHub. I don't know if we have time for a few questions. Or...
Thank you. Yes, I think we have time for a few questions. Yeah, good.
Thanks for the interesting talk. So you have already mentioned that the complexity is quadratic. Given this fact, so have you considered multi-key homomorphic encryption?
Yes. To be honest, it could be used. It's something different. Actually, we didn't want to be encrypted in a way. We wanted to split the secrets, but the fellows from Flower, I think yesterday already mentioned that they will do support homomorphic encryption and SMPC. I'm not sure if it will be peer-to-peer though. It's another point of view to look at the same problem. As this implementation was performed in the framework of Synthema, which is the Horizon 2020 European project, it was a very specific requirement from the project.
But the advantage of your approach is that it is unconditionally secure, at least
that's true.
At that site, but you won't get it from
because every encryption, theoretically at least, can be broken given enough resources, as we say in security. So SMPC, it's
your approach.
Yes, it's more difficult to break it, even with the significant resources.
All right. Sorry. Good.
So thank you for your presentation and for your interesting works. So my question was about the secret sharing algorithm. Which is the secret sharing algorithm you use?
So we use additive secret sharing. We do know that there are other SMPC schemes such as Samir's SMPC, etc. So it's very simplistic. So we do break it by drawing, let's say, the parts from a distribution, and we just ensure and look that they add up to the value of the actual parameter.
Okay.
So this is how it works.
But have you some constraint about the type of parameter that you trained? So should you use some quantization type? Because in general, in secret sharing algorithm, you are constrained to integer types.
Yes, that's true. There are a few ways to tackle with this. The easiest one is to multiply by a certain factor in order to convert the floats to integers, and then use the tools from modular arithmetic in order to secure it.
Have you some accuracy degradation, I guess? Because when you multiply by a factor, you lost something, you truncate the float.
We do multiply by a certain factor that ensures that we will not lose.
You don't lose at all?
There are ways to estimate the appropriate factor in order to lose as little as possible. And then at the server, before the aggregation, we do divide by the same factor in order to keep the scale, to maintain, to recall and maintain the scale.
Thank you very much.
Thank you very much for your talk. I checked your slides, mentioned your solution just resilient to the collision. So I'm just interested the motivation of why you just consider the resiliency to collision in medical AI. But because I feel in medical AI area, just the patients or the doctor inherently has sufficient motivation to truthfully report their data. Quite low possibility to provide some untruth data results to the central aggregation server. Yeah.
Okay, so in our case of the simple additive secret sharing, even if one out of the n peers is not malicious, it is we cannot exactly reconstruct the secret. This is why it is this resilient to attacks. Only if all actors are malicious under the simple additive secret sharing scheme, they can reconstruct the secret. However, if we do consider such a network where all peers are malicious, then to my way of thinking, it is like malicious becomes the ground truth.
Yes.
So only in this extreme case, security or privacy or the health, let's say, of the model is at risk.
Makes sense. Thanks.
Thank you very much.